Welcome back to week 3 of Logic, Language and Information 2. In this lesson, I'm going to explain how we use the rules for trees for first-order predicate logic to construct tree proofs, to construct models, and to classify formulas and test arguments. So let's begin. The crucial concept in a tree is the idea of an open or a closed branch. A branch in a proof tree is closed if it contains a formula and its negation, and if it's not closed, it's open. And a partially developed tree is what you have when you start from some set of formulas and process them to some extent using the tree rules. So a partially developed tree for a set sigma of formulas is a proof tree starting from that set sigma, where every formula is either in the starting set or follows from formulas higher up in the tree by way of the rules. Now, these are the standard concepts for trees, and they should be familiar to you if you've done propositional logic. Things get more complicated when we look at the specifics of the quantifier rules. If a tree stays open, we want to use that open branch in the tree to make a model. And for that, we need to make sure that there's no hidden contradiction in the formulas in the tree. We need to develop every complex formula to extract all of the information, because that's how trees work. Now, this is straightforward for the propositional connective rules, for things like conjunction, disjunction, the conditional, the biconditional or double negation. You just make sure that each of these rules have been applied and you're done. So they're easy. It's also straightforward for the particular rules in first-order predicate logic, the rules for the existential quantifier or the negated universal quantifier. These just have to be processed, introducing a new name for each formula, because if the branch says that something has property F, then we need to have something in our model with that property. So processing the existential quantified formula will ensure this. But the general quantifier rules are a little bit more powerful, and we need to be a bit more careful with them. So, if we have something like everything has property A on the branch, for it to be true in the model that we're constructing, we need to make sure that every instance of that formula for the model is true in that branch. So we need to make sure that we need every instance occurring in the branch. Similarly, if it's not the case that something has property A is on the branch, for that to be true in the model, we need every instance of A to be false in that model for every name that occurs in that branch. That is, we need every instance of not A to end up being true in the model. So, in a complete open branch, the easiest thing to do is to just substitute every name that occurs in that branch into each of the general formulas in that branch. And it turns out that that's enough. If those names name all of the things that there are, then these instances are going to be enough to make those general formulas true. So here's the rule, here's the definition of a completely developed open branch in a predicate logic proof tree. It's completely developed if and only if every resolvable formula that's been resolved has been resolved. That is, every complex propositional formula, every existentially quantified formula, and every negated universally quantified formula has been ticked off. They've been processed. And for every name and for every general formula in the branch contains one instance of the general formula with that name. And finally, and this is a special condition for that special case where we don't actually have any names in the branch, each general formula in the branch has had a name substituted into it at least once. You can't get away with not doing any substitutions because you haven't used any names. Finally, a tree is completely developed if and only if each open branch in the tree has been completely developed. And so that's the definition. Now, it's quite hard to understand that definition in the absence of an example, so let's look at an example now. Here's a question for you. Take a look at this tree. I can tell you now that there are no mistakes in the tree. Every step is okay. But is it fully developed? What do you think? How did you go? I hope you got it right. This tree is not fully developed. It's not completely done. If you take a look at this negated existentially quantified formula here, it's not the case that something has got property G. This has been processed with A, but not with B, even though B occurs in this left branch. The right branch is closed. You don't need to worry about that. The left branch, though, is open, And we've got a B over here that we haven't substituted here. So let's make that substitution. And now the tree is complete. Every complex formula has been processed. We'll start from the top. This formula, something is such that if it's F, it's G. That's been ticked with an A. This negated conditional, that's been processed. This instance, FA implies GA, that's been processed. Something is F, that's been processed with a B. Now this negated existential, that's been had A and B substituted into it. And the other things are either atoms or negated atoms. So the names A and B are the only names that occur in this branch, and they have both been substituted in the only general formula here. So this is a complete branch that I've now got marked in red. Let's see what this branch says about the world. The objects that this mentions are A and B. So we could just select the domain to be the objects A and B. And then we can see what the predicates say about A and B. If the world contains these objects, here's how this branch says we should interpret the predicates F and G. So we want to interpret F and we want to interpret G as talking about the objects A and B. So we get a little table like this, and we see that the open branch says that FA is false. So we'll assign a value 0 here to F on A, and FB is true according to the formula here, so I will assign FB the value true. We'll do the same thing for G. We've got GA, the negation of GA in the branch, so GA wants to be false, and we've got the negation of GB in the branch, so we'll write GB is false. And that is enough to make every formula in this tree true. This is a model, and we can check, these formulas, not FA, not GA, FB, not GB, they are all true. That's what these values, false, 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 and true, are designed to do. And if you step up the tree backwards, you can see that these formulas are also going to be true. Nothing has property G. We've done the A and the B instances here, and you can check, indeed, that this model says that nothing has property G because A doesn't and B doesn't. On the other hand, something has property F, that's true. You can see, indeed, that B is the thing with property F, as you'd expect, because we made the substitution for B. FA implies GA is true because we split into two cases and we've taken the not FA case, so this not FA, FA is indeed false, and that's why this conditional FA implies GA is true. Finally, the starting two formulas, this negated conditional formula is indeed true because we made the antecedent something is F true, and the consequent something is G, we made that false. And in the last case, something is such that fx implies gx. That's true because the A instance is true right here. So indeed, everything in this branch turns out to be true. This means, for example, that if I was having an argument which started with this first formula as a premise and this formula, if something is F, then something is G, as the conclusion, that argument is invalid because we have a model that makes the premise true but makes the conclusion false because it makes its negation true. So in this example, we went from a complete open branch to a model. That was one case. Here's what we actually did when we did this. What did we choose for the domain for the model? We chose one object for each name in that open branch. Now, the easy way to do this is to do what we just did. Use the collection of names as the domain itself. The names were A and B, and we say the objects are A and B. This, in effect, makes every name in the tree a standard name, and it works just fine. For the predicates, what we did is, if something like FA occurred in the branch, we interpreted F as applying to A. That's the one in the table for the value interpreting F on A. Having a 1 in that spot says that F does apply to A. On the other hand, if not FA occurs in the branch, we interpret F as not applying to A, and that's the 0 in the table interpreting F in the A spot. Now what about if neither FA nor not FA occur in the branch? This means that we don't need FA to be true and that we don't need FA to be false. And that means you can choose. You can choose whatever you want. 1 or 0, either would be fine. What happens if both FA and not FA occur in the branch? What could you do then? Because you couldn't assign it a 1 and a 0. Well, that can't happen because the branch is open. It's not closed. So we never have a formula and its negation. We could never have FA and not FA in the branch. So the result of this process is a model which in fact will make every formula in the branch true. Now we've seen one example of using a tree to test an argument. We can use trees to test arguments and classify formulas in general. Here's what you do. If you want to know whether an argument from premises to conclusion is valid, you process a tree for the premises and the negation of the conclusion. If the tree is closed, the argument is valid, and that's where we write X turnstile A to say that that argument is valid, and we proved so using a tree. On the other hand, if the tree stays open, the argument is not valid, and we write down X/turnstile A to say that the argument is not valid, and we could use this open branch to construct a counter model, a model which makes the premises true and the conclusion false. If I wanted not to test an argument, but to show whether or not a formula was a tautology, I'd process the formula, its negation. I'd process a tree for not A. Why is that? Because if the tree closes, that means you cannot make not A true. And so, indeed, if not A can't be true, that means A can't be false, and it's a tautology. And we'll write turnstile A with a single turnstile to say that we have shown that A is a tautology, or if you like, we've proved A. A can be proved on the basis of no other assumptions. It's like an argument with no premises. On the other hand, if that tree for not A doesn't close, if it's open, then it's not a tautology, so we can slash the turnstile in front of the A, and we could use that open branch as a way of making not A true. That would be a way of making A false, which would indeed show that it wasn't a tautology. Finally, if you wanted to show that a formula was a contradiction, you could process a tree for that formula itself. And if the tree closes, then indeed it's a contradiction because you can't make it to be true. So this time we write A with a turnstile behind it to say that we could never make A true. It's inconsistent or a contradiction. On the other hand, if the tree stays open, then I've got a way of making A true, and it's not inconsistent, it's not a contradiction. So we slash the turnstile, but this time with A on the other side. So in general, if I'm processing a tree, the things on the left-hand side of the turnstile are the things I'm trying to make true. The things on the right-hand side of the turnstile are the things I'm trying to make false. So that's how we use trees to classify arguments. That's everything you need to do to start using trees for first-order predicate logic. In the next lesson, I'll give you 3 examples so you can see lots of different features of how trees work.